All right, so now we're going to prove that our definition of prime agrees with the standard way of defining prime. So this more algebraically friendly way of defining a prime number is in agreement with how we know how things should work. So again, when we say P is prime, we mean that P divides AB tells us P should divide A or P should divide B. That's our definition of prime. So what this lemma is saying, which is called Euclid's lemma, one way of expressing Euclid's lemma, is that P is prime if and only if whenever we have a divisor M of P, that divisor is P or that divisor is 1. So the only factors of P are 1 and P, and since P is bigger than 1, 1 is not equal to P. So we're first going to show that our definition implies the usual one, and then we'll go backwards. So the forward direction, we're going to assume P is prime, and we have a divisor of P. We want to show that P is M or M is 1, or M is P or M is 1. Since M divides P, P is a product of A and M for some natural number A. We also know that A and M, since they're divisors of P, are smaller than P. But we can use this equation to deduce that P divides AM because AM is P times 1, so P goes into the left-hand side. So P divides this product. By the definition of prime, whenever P divides a product, P divides one of the terms in the product. Okay, so we're going to go into cases now. If P divides the first term in the product, then, well, P is a divisor of A, so it's smaller than A, smaller than or equal to A. But A was also smaller than or equal to P. And the only way for those both to be true is if A and P are equal. Because if I'm less than or equal to something and bigger than or equal to something, I must be equal to that something. And if A is equal to P, then it must be that M is 1. Great, so M is 1, that's an acceptable outcome. Now let's look at what happens in the second case when P divides M. If P divides M, then exactly an analogous argument, P is going to be less than or equal to M, but M is less than or equal to P, so P equals M, and that's this other acceptable outcome. And that's our forward direction. For the backwards direction, we're going to assume whenever we have a divisor of P, M is 1 or M is P. We're going to suppose that P is not prime. You don't have to go by contradiction for this. You can say be such that P divides AB and P does not divide B. So you don't actually need this part, but I phrased it as a contradiction for this particular video, and we'll carry out with that. So suppose that P is not prime, that is, P divides a product, but it doesn't divide either of the terms in the product. Since P doesn't divide the second term, B, the greatest common divisor of P and B is some number M less than P. Why is it less than P? Well, it's a common divisor, and P doesn't divide B, so it can't be equal to P, so it has to be less than P. All right, great. So M divides P because it's a common divisor of both of them. Since it's a divisor, it's less than P, and it's less than P, it must be equal to 1 because that's our assumption. Whenever we have a divisor of P, it's either 1 or P, but it's less than P, so it has to be 1. So this tells us that the GCD of P and B is 1. Well, we can find Bezier coefficients, x and y, such that px plus by is the greatest common divisor of P and B. In this case, the greatest common divisor is 1, so we can find integers x and y such that px plus by is 1. Then we're going to do a trick. We're going to multiply through by a. When we multiply through by a, we get this expression here. And let me notice something. P divides this first term, and P divides the second term in the sum. We proved in class, or you all proved in class, that when P divides two terms of a sum of an expression like this, P has to divide the remaining one. So we deduce that P divides A from this, which contradicts P does not divide A. So this couldn't have happened, so P is prime. Now technically we don't need this. Again, we don't have to go by way of contradiction if we don't want to. we can get rid of this statement I wrote here. And then from this, we'll deduce that P divides A, and we just get rid of the word a contradiction.